Welcome back to the Bizarre Bureau, where we peel back the layers of reality to glimpse the strangest truths underneath. What if I told you that an action you take right now could change something that has already happened? No, this isn't science fiction. It's one of the most mind-bending, reality-twisting concepts in all of physics, the quantum eraser paradox. Can the future truly rewrite the past? Buckle up, because we're about to dive deep down the rabbit hole. To understand how the future might influence the past, we first need to visit the past of quantum mechanics itself. Let's talk about the famous double-slit experiment. Imagine you have a wall with two thin, parallel slits in it. You start firing tiny particles, like electrons, one by one at this wall. On the other side, you have a detector screen that records where each particle lands. Now, if you close one slit and fire the electrons, they land on the screen in a single band right behind the open slit. Makes sense, right? It's like throwing tennis balls through a hole in a fence. But when you open both slits, something truly bizarre happens. Instead of two bands, you get a whole series of bands and interference pattern. This is classic wave behavior. It's as if each single electron, traveling alone, somehow passes through both slits at the same time, like a wave, and then interferes with itself before hitting the screen. This is the heart of wave-particle duality. A quantum particle, like an electron or a photon, exists in a superposition of all possible states at once. It's both a particle and a wave in all possible locations until we measure it. The very act of observation forces it to choose a single state. The moment we try to find out which slit the particle went through, the interference pattern vanishes. It's as if the particle knows it's being watched and decides to behave like a well-mannered particle, going through only one slit. This is called collapsing the wave function. So we have a rule. If we know the which path information, which slit the particle went through, we lose the wave-like interference pattern. If we don't know, we get the pattern. Simple enough, right? Well, this is where things get truly strange. The quantum eraser experiment takes this one giant leap further. Imagine we set up the double-slit experiment again, but this time with photons, which are particles of light, and we get clever. We decide we're going to try and peek at which slit each photon goes through, but in a very subtle way. We'll tag them. We do this using a special type of crystal placed right after the slits. When a photon passes through, this crystal splits it into two entangled photons. Think of them as quantum twins. Whatever happens to one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. So now, for every original photon that goes through the slits, we have a pair, a signal photon that continues on to our main detector screen, and an idler photon that travels off in a different direction. Here is the key. The path of the idler photon contains the information about which slit its signal twin went through. If we can detect the idler photon, we can know the path of the signal photon. Let's call the main screen detector A. The idler photons are sent towards a separate setup with its own set of detectors. Let's call them B, C, and D now. If we simply detect the idler photons and record their path, we gain the which path information for their signal twins. And just as we'd expect, when we look at the results on detector A, the interference pattern is gone. We see just two clumps, as if the photons were simple particles. By knowing the path, we destroyed the wave behavior. No surprises there. But now we introduce the eraser. This is where your brain might start to melt. The setup for the idler photons is designed to be much farther away than the main screen. Detector A. This means the signal photon will hit detector A before its entangled twin, the idler photon, even reaches its own detectors. Now, let's look at the idler setup. We use a series of beam splitters that essentially scramble the path information. An idler photon arriving at, say, detector B or C could have come from either slit. There's no way to tell. In other words, by detecting a photon at B or C, we have effectively erased the which path information. We've chosen to become ignorant again. The idler photons that go to another detector, detector D, however, still carry the path information. So here's the paradox. The signal photons arrive at detector A one by one, and when we look at the complete pattern, it's just a random-looking scatter. No interference. But then, long after those photons have already landed and their positions recorded, we look at where their idler twins ended up. We separate the data from detector A into groups. First, we look only at the signal photons whose idler twins landed on detector D, the ones where we know the path. As expected, their pattern on detector A is just two clumps. No interference. But now, for the mind-blowing part. We look at the signal photons whose idler twins landed on detectors B or C, the ones where the path information was erased. When we isolate just those specific photons on detector A, a ghostly interference pattern emerges from the noise. Let that sink in. The choice we made after the signal photon had already hit the screen, the choice of whether to keep or erase the path. Information seems to have retroactively determined how that photon behaved in the past. It's as if the photons that would later have their path, information erase, knew it in advance and decided to act like waves, creating an interference pattern. And the photons that would have their path information preserved knew it too and acted like particles. This is the quantum eraser paradox. How can a future event, the measurement or erasure of the idler photons, path change a past event, the behavior of the signal photon at the slits? This seems to violate causality, the fundamental principle that cause must always precede effect. So, does the future rewrite the past? Well, not exactly in the way you might think. We can't use this to send lottery numbers back in time. The key is that we can only see the interference pattern after we've looked at the results from the idler detectors and sorted the data. Looking at the total combined pattern on detector A before sorting gives us no information. It's always just a scattered mess. The complete information, the full picture of reality, only emerges when we bring together all the data from all the entangled parts of the experiment. The paradox arises from our very human way of thinking about time as a simple linear street. In the quantum world, things are not so straightforward. One interpretation is that a quantum system isn't real in a classical sense until the entire measurement is complete. The photon doesn't decide to be a wave or a particle at the slits. The entire experimental setup, including the future choice of erasing information, must be considered as a single indivisible quantum event. The story of what happened is only written once all the information from all points in space-time is brought together. Another way to think about it is that there is no rewriting. The potential for both patterns, the interference and the non-interference, exists simultaneously within the data. Our choice of how to sort the idler photons simply reveals one pattern or the other that was hidden there all along. It's not changing the past. It's choosing which version of the past we get to see. The quantum eraser experiment challenges our deepest intuitions about reality, time, and causality. It shows us that the universe at its most fundamental level is far stranger and more interconnected than we could ever imagine. An event here and now can be inextricably linked to an event over there and later. It suggests that our classical notions of past, present, and future might just be an illusion, a convenient story we tell ourselves to make sense of a world that is, at its core, a bizarre and beautiful quantum enigma. What do you think? Is this proof that time isn't as linear as it seems? Or is it just a quirk of measurement that says more about our knowledge than about reality itself? Let me know your thoughts down in the comments. Thank you for joining me on this journey into the bizarre. If you enjoyed having your reality questioned, please hit that like button and subscribe to the Bizarre Bureau for more explorations into the unknown. We'll see you in the next one.